What if something from another star system changed Mars forever, and we're only now beginning to understand what happened? For the first time in recorded history, an object born in the darkness between alien suns swept past the red planet at a distance so close that every major space agency on Earth held its breath. This wasn't just another flyby. This was an encounter that defied probability, challenged our understanding of planetary interactions, and left behind questions that still haunt the scientific community today. The visitor's name was 3I Atlas, and what it did to Mars might have rewritten the rules of our solar system in ways we never imagined possible. You're about to discover evidence that scientists are still analysing, mysteries that refuse simple explanations, and a cosmic event so rare that some researchers believe we won't see anything like it again in our lifetimes. Stay with me. In the next few minutes, we're going to explore the most unprecedented interstellar encounter Mars has ever experienced. What happened during those critical hours, what changed in the Martian environment, and what it all means for our understanding of how worlds can be touched by visitors from the vast cosmic ocean beyond our Sun. If you've ever wondered whether a single object from another star could alter the fate of an entire planet, you're in the right place. Hit that like button right now, and drop a comment telling me what you think really happened when 3I Atlas swept past Mars, because what I'm about to share with you will challenge everything you thought you knew about planetary encounters. Imagine standing on the surface of Mars beneath a salmon-pink sky, dust devils twirling in the distance across ancient valleys that once held oceans. The thin atmosphere whispers against canyon walls carved by water that vanished billions of years ago. Everything feels timeless, unchanged, locked in a geological sleep that has lasted longer than human civilization has existed. Then something appears in that sky. Something that doesn't belong. Something that was never supposed to be there. An interloper from beyond, carrying the chemical signature of another star system, moving on a trajectory that speaks of origins so distant that light from its birthplace hasn't reached Earth yet. This is the moment when Mars met 3I Atlas, and nothing about this encounter was ordinary. The date itself felt surreal to those tracking the comet's path. Scientists had calculated the trajectory weeks in advance, running simulation after simulation, triple-checking the numbers because the odds seemed impossible. Comets from interstellar space are rare enough. We've only confirmed a handful in all of human history, but for one to pass this close to a planet in our solar system, the probability calculations made veteran astronomers shake their heads in disbelief. Some researchers later admitted they kept rechecking their work, convinced there had to be an error somewhere in the orbital mechanics. There wasn't. The universe had arranged something extraordinary, and Mars was about to experience what no human eye would ever directly witness, an intimate encounter with an object forged in the cold darkness between stars, carrying ice and dust from a stellar nursery we can only dream about. What makes this moment so profound isn't just the rarity, it's what it represents. Think about it. Every atom in your body, every molecule of air you breathe, every grain of sand on every beach on Earth was born either in our Sun or in stars that died before our solar system formed. We are made of stellar material, but that material has been processed, melted, reformed, and integrated into the fabric of our cosmic neighbourhood for over 4.5 billion years. Everything around us shares a common heritage, a common chemistry, a common story written in the language of solar system formation. But 3I Atlas? It carried a different story. Its ice froze around a different star, its dust condensed from a different nebula. The organic molecules within it, and scientists suspected there were organic molecules, formed under conditions we can only theorize about. When this visitor approached Mars, two entirely separate threads of cosmic history were about to intersect. The hours leading up to closest approach created a strange tension in observatories around the world. You have to understand what this meant for the teams tracking the encounter. These weren't people prone to hyperbole or sensationalism. These were men and women who had spent careers studying orbital mechanics, atmospheric chemistry, and planetary science with the kind of patient precision that defines modern astronomy. They deal in facts, measurements, spectra, and data. Yet even among these professionals, there was an undercurrent of something that felt almost like anxiety. Not fear. Nothing about 3I Atlas posed any threat to Mars or Earth, but rather the weight of witnessing something that might never happen again. The pressure to capture every possible piece of data, to miss nothing, to ensure that this fleeting moment would be preserved in the permanent record of human knowledge. Because here's the truth that kept everyone awake during those critical tracking windows. If we failed to document this encounter properly, future generations would never forgive us. Mars itself had no awareness of what was coming, of course. The planet continued its eternal rotation, its thin carbon dioxide atmosphere cycling through seasonal changes, its polar ice caps expanding and contracting with the Martian year. Dust storms swept across the equatorial regions, some small and localized, others massive enough to engulf entire hemispheres. The planet's two tiny moons, Phobos and Deimos, continued their rapid orbits, casting swift shadows across the rust-coloured landscape. Somewhere in the ancient riverbeds and crater floors, the Curiosity and Perseverance rovers went about their programmed tasks, drilling samples, analysing soil, searching for signs of ancient microbial life that might have thrived when Mars was young and wet and warm. The planet existed in its routine, unaware that something unprecedented was approaching from the direction of the outer solar system, inbound on a hyperbolic trajectory that would bring it closer to Mars than many of the planet's artificial satellites. The magnitude of what was about to happen becomes clearer when you consider the distances involved. Space is vast beyond human comprehension, and even within our solar system the gaps between worlds are enormous. Mars orbits the Sun at an average distance of over 200 million kilometers from Earth. The interstellar visitors we've detected, Oumuamua before 3I Atlas and others potentially still undetected, travel through the solar system on paths that typically keep them far from any planetary encounters. The simple geometry of it makes close approaches statistically unlikely. The solar system is mostly empty space, with planets occupying tiny fractions of the total volume. For an interstellar object to not just pass through our cosmic neighbourhood, but to actually come within striking distance of a major planet requires an alignment of trajectory and timing that borders on the miraculous. And yet here it was, happening in real time, with the entire astronomical community watching. What did those watching expect to see? The honest answer is that nobody knew for certain. Previous interstellar objects had given us some clues about what to look for: unusual outgassing patterns, unexpected brightening, chemical signatures that didn't match solar system comets. But every prediction came wrapped in uncertainty because the sample size was so small. We had barely begun to understand these cosmic wanderers, and now one was about to interact with a planetary environment in ways we could actually measure. Would 3I Atlas shed material that would enter Mars's thin atmosphere? Would there be any detectable change in the planet's exosphere, that tenuous outer layer where atmospheric gases gradually transition into the vacuum of space? Could there be electromagnetic effects, perhaps interactions between the comet's plasma tail and Mars's weak magnetic field? The questions multiplied faster than anyone could formulate proper hypotheses. Some researchers allowed themselves to imagine more dramatic possibilities, though always carefully framed as speculation rather than prediction. What if the encounter triggered changes in Mars's atmospheric chemistry, subtle alterations that instruments might detect, temporary disturbances that would fade but leave behind data about how planetary atmospheres respond to interstellar material? What if dust or gas from 3I Atlas actually reached the Martian surface, depositing molecules from another star system onto the rust-coloured plains? The thought was intoxicating, almost too good to be true. Imagine collecting samples from Mars years from now and finding within them trace amounts of material that originated beyond our Sun's influence, carried there by a cosmic visitor during one brief shining moment of intersection. It would be like finding a message in a bottle, except the bottle travelled between stars and the message was written in the language of interstellar chemistry. The closer 3I Atlas came, the more the tension built. Observatories coordinated their schedules, ensuring continuous coverage across multiple wavelengths of light. Radio telescopes listened for any unusual emissions. Spacecraft orbiting Mars, the tireless robotic sentinels that had been studying the red planet for years, received new instructions, their instruments recalibrated to focus on this unexpected opportunity. Every telescope that could be spared from other observations turned its attention to the space between Mars and the approaching visitor. The astronomical community had transformed into something resembling mission control during a critical phase of a space mission, except this mission had been arranged by the universe itself, and humanity was along for the ride as witnesses rather than participants. Then came the moment of closest approach, measured not in the comfortable distances that usually separate cosmic objects, but in terms that made the encounter feel visceral and immediate. For a brief window of time, 3i Atlas and Mars shared the same region of space, close enough that if you could somehow stand at a vantage point far above the ecliptic plane and look down on the solar system, you would see them as neighbouring dots. Impossibly close by astronomical standards, close enough that whatever gas and dust the comet shed would be measured not in terms of where it might theoretically reach, but where it definitely would reach. Close enough that the gravitational influence of Mars, though small compared to Jupiter or the Sun, would subtly alter the comet's trajectory, bending its path in ways that would change where it travels next in its journey through the galaxy. What happened during those hours? The full picture would take months to emerge from the data, but even in real time, observers knew they were witnessing something significant. The comet brightened slightly as it rounded the Sun earlier in its trajectory, a sign of outgassing as solar heat vaporized ancient ice. That gas and dust, material that had been frozen since before our Sun ignited, now spread out along 3i Atlas's orbital path, creating a faint tail that instruments could detect, even if human eyes couldn't see it without powerful telescopes. As Mars and the comet converged, that tail swept across the space where the planet travelled. Did molecules from 3i Atlas touch Mars's atmosphere? Did dust grains originally forged around another star enter the Martian exosphere? The instruments were collecting data, photons were being captured, spectra were being recorded. The encounter was happening, being documented in real time, and yet the full implications wouldn't be understood until scientists could spend months analysing what their instruments had captured. There's something profoundly moving about this moment when you really sit with it. Mars has existed for over 4 billion years, spinning through space, bearing witness to the slow evolution of our solar system. It has survived asteroid impacts that would have sterilized any life on its surface. It has endured the gradual loss of most of its atmosphere, transforming from a warm, wet world into the cold desert we see today. It has been studied by dozens of spacecraft, mapped in exquisite detail, analysed with instruments sophisticated enough to detect individual atoms in Martian soil. And yet, in all those billions of years, in all that time bearing witness to cosmic history, this encounter with 3i Atlas represented something genuinely new. A visitation from beyond, a touch from another stellar neighbourhood, a cosmic handshake between worlds that formed under different suns. If Mars could speak, what story would it tell about the moment when something from the interstellar deep swept past, briefly shared its space, and then continued on into the darkness beyond? The researchers watching felt the weight of that story even if they couldn't yet fully articulate it. They understood, perhaps more clearly than anyone, that they were documenting a moment that transcended ordinary planetary science. This wasn't just about orbital mechanics or atmospheric chemistry, or the composition of an interstellar comet. It was about connection. The discovery that our solar system isn't isolated, that visitors do arrive from the cosmic ocean beyond our sun's sphere of influence, and that sometimes, against all odds, those visitors pass close enough to our worlds that we can study them, learn from them, and add their story to our understanding of the universe. 3i Atlas came from somewhere we can't even precisely identify, travelled for who knows how long through the space between stars, entered our solar system on a trajectory that would never repeat, and in one brief moment of cosmic choreography, danced past Mars close enough that the encounter would be remembered as long as human civilization records astronomical events. As the moment of closest approach passed, and 3i Atlas began to recede, travelling outward toward the outer solar system, and eventually back into interstellar space, the immediate tension in observatories gave way to a different kind of pressure, the realization that the real work was just beginning. The data had been collected, but data without analysis is just numbers and images. The true story of what 3i Atlas did to Mars would emerge slowly, carefully, through the patient work of researchers who would spend months examining every spectrum, every image, every measurement captured during those critical hours. And as that story began to unfold in research papers and conference presentations, it would become clear that this encounter had indeed changed something, not just about Mars, but about our understanding of how planets and interstellar visitors interact, how rare events can provide common insights, and how the universe occasionally arranges moments so extraordinary that they remind us why we look up at the sky and wonder. The discovery that 3I Atlas would pass remarkably close to Mars didn't happen in isolation, and the response certainly didn't come from a single organisation working alone. Within hours of the refined trajectory calculations that revealed just how close the encounter would be, a cascade of communications began flowing between space agencies on 3 continents: NASA's Jet Propulsion Laboratory in California, the European Space Agency's Operations Center in Germany, and the China National Space Administration's Deep Space Network all recognized simultaneously what this opportunity represented. The usual boundaries that sometimes exist between national space programs, differences in priority, competition for resources, the simple friction of coordinating across time zones and languages, all of that evaporated in the face of a shared recognition that something unprecedented was about to happen. The timing, however, couldn't have been more complicated. When the final trajectory projections confirmed the close approach date, NASA was operating under significant constraints. The partial government shutdown that had affected various federal agencies was creating ripple effects throughout the space program, not completely halting operations but certainly complicating them. Key personnel were furloughed or working under uncertain conditions. Decision-making processes that normally moved with practiced efficiency were slowed by bureaucratic complications. Resources that would typically be available for rapid response observing campaigns were tied up in administrative tangles. In any other circumstance, these obstacles might have delayed or limited NASA's response to the 3I Atlas encounter, but this wasn't any other circumstance. The career scientists and engineers at NASA understood that opportunities like this don't wait for bureaucratic problems to resolve themselves. The universe doesn't care about government shutdowns, and if humanity wanted to document this encounter, it would have to find a way despite the challenges. What emerged from this crucible of necessity was something remarkable, a level of international cooperation and creative problem solving that demonstrated what space exploration can be when the stakes are high enough and the goal is clear enough to cut through institutional barriers. The European Space Agency stepped up its contribution to the observing campaign, offering to coordinate tracking efforts and share data in real time. ESA's Mars Express orbiter, which had been studying the red planet for years, was in an excellent position to observe the encounter from Martian orbit. The spacecraft's suite of instruments, originally designed to study Mars's atmosphere, geology, and magnetic field, could be repurposed to focus on the space around the planet during the 3I Atlas flyby. Engineers worked through the night to revise command sequences, ensuring that Mars Express would be looking in the right direction at the right time with the right instruments active. China's contributions added another layer to the coordination effort. The CNSA had been building its own impressive deep space exploration program, and the agency offered access to its tracking stations and data analysis resources. Chinese astronomers had been following 3I Atlas since its discovery, and research teams in Beijing and Shanghai had developed models predicting how the comet might behave as it approached the inner solar system. Sharing those models with NASA and ESA researchers created a more complete picture of what to expect, allowing all parties to refine their observing strategies. The data-sharing agreements that were hammered out during those intense planning sessions set precedents for future international cooperation, proving that when the scientific stakes are high enough, institutional and political differences can be set aside in favour of the larger goal of advancing human knowledge. But the real heroes of this coordinated effort weren't the administrators negotiating data-sharing agreements, or the diplomats facilitating international cooperation. They were the men and women who operate spacecraft, maintain orbital assets, and squeeze every possible observation out of instruments that were never specifically designed for this kind of opportunity. Think about the pressure these teams were under. They had one chance, one brief window when 3I Atlas would be close enough to Mars that detailed observations would be possible. Miss that window, make a mistake in the command sequences, have an instrument malfunction at the critical moment, and the opportunity would be lost forever. 3I Atlas wasn't going to come back around. Its hyperbolic trajectory meant it would pass through the inner solar system exactly once before heading back into interstellar space, never to return. Every observation had to count, every decision had to be correct. The margin for error was zero. The spacecraft themselves represented decades of engineering, billions in investment, and the accumulated expertise of thousands of people who had designed, built, launched, and operated them. NASA's MAVEN mission, designed to study Mars's upper atmosphere and how it interacts with the solar wind, found itself perfectly positioned for a completely different kind of observation. The spacecraft's instruments could detect gases at extremely low concentrations, making it ideal for hunting for any trace of material from 3I Atlas that might enter Mars's exosphere. Engineers recalibrated MAVEN's ultraviolet spectrograph, the instrument that normally maps how solar radiation affects Martian atmospheric gases, to look for the specific spectral signatures expected from cometary material. If even tiny amounts of hydrogen, oxygen, or carbon from 3I Atlas reached Mars's upper atmosphere, MAVEN should be able to detect it. The Mars Reconnaissance Orbiter, NASA's high-resolution imaging platform that had been mapping the Martian surface in stunning detail for years, received new targeting instructions. While MRO's cameras were designed to look down at the planet's surface, they could also be pointed towards space if the opportunity warranted it. The team calculated whether the comet would be bright enough and positioned favourably enough for MRO to capture direct images. The answer was yes, but just barely. The window of opportunity would be measured in minutes, and the spacecraft would need to execute a carefully choreographed series of manoeuvres to point its cameras at precisely the right time. Mission planners spent days working through the details, accounting for every constraint: power limitations, thermal considerations, communication windows with Earth, the need to not disrupt other ongoing observations more than absolutely necessary. The final command sequence was a masterpiece of precision, every action timed to the second, every contingency anticipated. ESA's Mars Express added its own unique capabilities to the observation campaign. The spacecraft's high-resolution stereo camera, normally used to capture detailed images of Martian surface features, was tasked with attempting wide-field imaging of the encounter. The hope was to capture context, to document not just 3I Atlas itself, but the space around Mars during the closest approach, providing a visual record that would help researchers understand the geometry of the encounter. Additionally, Mars Express carried a radar instrument designed to probe beneath the Martian surface looking for subsurface water ice. While radar wouldn't directly contribute to comet observations, the data it collected during the encounter period would provide a baseline, a snapshot of Mars's subsurface conditions at the precise moment of the interstellar visitor's passage. If future observations detected any long-term changes, this baseline data would be invaluable for determining what had changed and what remained the same. The coordination extended beyond spacecraft in Mars orbit. Ground-based telescopes around the world, representing institutions from dozens of countries, coordinated their own observing campaigns. The challenge with ground-based observations was that Mars and 3I Atlas would only be visible from certain locations at certain times. An Earth's rotation meant that no single observatory could maintain continuous coverage. The solution was a relay system. As the encounter region set below the horizon for observatories in Chile, telescopes in Australia would pick up the observation, followed by facilities in Hawaii, then California, then Spain, creating an unbroken chain of coverage that spanned the globe. Professional astronomers coordinated with amateur observers who had contributed valuable data throughout 3I Atlas's journey through the inner solar system. Everyone who could contribute did so, creating a collective effort that transcended the usual divisions between professional and amateur, between large institutions and individual enthusiasts. What drove this extraordinary mobilization? It wasn't just scientific curiosity, though that was certainly part of it. There was also a sense of responsibility, a recognition that humanity had been given an opportunity to witness something remarkable, and with that opportunity came an obligation to document it as thoroughly as possible. The researchers coordinating these efforts understood that they were working not just for themselves or even for the current generation of scientists, but for future generations who would inherit the data and build upon it. 50 years from now, 100 years from now, researchers will still be studying what happened when 3I Atlas passed Mars. The quality and completeness of the observations made during those critical hours would determine how much future scientists could learn. That kind of long-term thinking, that sense of working toward a goal that extends far beyond any individual career or even any individual lifetime, is what makes large-scale scientific cooperation possible. As the moment of closest approach drew near, the tension in mission control centres and coordination rooms reached a peak. Engineers monitored spacecraft telemetry, watching for any sign of problems that might disrupt the carefully planned observations. Scientists stood by to receive the first data transmissions, knowing that even preliminary information might reveal unexpected phenomena, requiring immediate follow-up observations. Communication links between facilities were tested and retested, ensuring that data could flow smoothly between spacecraft, ground stations, and analysis centers. Everyone involved understood that this was a moment that would define their careers, a moment that they would remember and talk about for the rest of their lives. The opportunity to participate in documenting a unique cosmic event comes rarely, even for people who dedicate their lives to space exploration. Many of the people in those control rooms had worked on Mars missions for decades and might never see anything like this again. And then it happened. The data started flowing in, first from MAVEN, as its ultraviolet instruments began detecting unusual signals in Mars's upper atmosphere, then from Mars Reconnaissance Orbiter, as its cameras captured images of a faint smudge of light that was 3I Atlas, visible against the background stars. Mars Express contributed its own observations, adding European perspective and capabilities to the growing dataset. Ground-based telescopes reported their observations, each adding another piece to the puzzle. Within hours, researchers had accumulated more data about this interstellar visitor's interaction with Mars than anyone had dared hope for. The instruments had worked. The coordination had succeeded. The universe had cooperated by not throwing any unexpected complications into the mix. Against considerable odds and despite significant obstacles, the international space exploration community had risen to the challenge and documented something extraordinary. The data existed now, preserved in archives, ready to be analysed, interpreted and understood. Tangible evidence that when 3I Atlas met Mars, humanity was watching, recording, and ensuring that the encounter would not pass unnoticed into history. The first images arrived with the kind of anticlimactic quiet that often accompanies genuinely historic moments. No dramatic countdown, no sudden gasps of amazement, just data packets transmitted across millions of kilometers of space, received by ground stations on Earth, routed through computer systems to the scientists waiting for them, and appearing on monitors as raw, unprocessed files that would need hours of work before their secrets would become clear. But for the researchers crowded around those monitors, even the raw images carried an electric charge of realization. They were looking at photons that had bounced off an interstellar object near Mars and travelled to Earth, carrying information that no human eye had ever seen before. The images were real. The data was solid. The encounter had been captured. Processing astronomical images isn't like applying an Instagram filter or adjusting the contrast on a photograph. It's painstaking work that involves removing noise, calibrating the response of individual pixels, accounting for spacecraft motion and pointing accuracy, combining multiple exposures to improve signal-to-noise ratios, and carefully extracting the faint signal of a comet from the background of stars and cosmic rays that contaminate every deep space image. The team working on the Mars Reconnaissance Orbiter images spent hours on these tasks, gradually coaxing clarity from data that initially looked like little more than static with a few brighter spots that might be anything. But as the processing progressed, as noise gave way to signal and random patterns resolved into coherent structure, the image of 3I Atlas began to emerge, a faint fuzzy patch of light surrounded by a subtle elongation that marked its developing tail, visible proof that the comet was actively shedding material as it moved through space near Mars. The emotional impact of seeing these images for the first time is hard to convey to anyone who hasn't spent years studying something that exists only as abstract data. Coordinates, spectra, brightness measurements. For the researchers who had been tracking 3I Atlas since its discovery, who had calculated its trajectory, predicted its behaviour, and advocated for the resources to observe its encounter with Mars, these images represented vindication and revelation simultaneously. Vindication that the effort had been worthwhile, that the predictions had been accurate, that the careful planning and international coordination had paid off. But also revelation, because images always reveal details that predictions miss. The exact brightness distribution in the comet's coma, the subtle asymmetries in how material was being shed, the precise orientation of the tail relative to Mars, all of these were details that could only be confirmed through direct observation. Theory and prediction could get you close, but only images could show you what really happened. What did those images reveal? Start with the basics. 3. I-Atlas appeared as a small diffuse object, much fainter than any comet you could see with the naked eye, but bright enough that spacecraft instruments could capture it clearly. The lack of a sharp, point-like nucleus told researchers that the comet was shrouded in a cloud of gas and dust, the coma that forms when cometary ice sublimates in the warmth of the inner solar system. The size of that coma provided clues about how actively the comet was outgassing, how much material it was losing, and therefore how much mass it must have contained to sustain that activity. The shape of the coma, slightly elongated in one direction, indicated the direction the solar wind and radiation pressure were pushing the release material, creating the beginning of a tail that stretched away from the Sun, and in this particular geometry, away from Mars as well, though the planet was close enough that some of that material would inevitably intersect with the Martian environment. The Mars Express images added a different perspective, literally. Because the European spacecraft was in a different orbit than NASA's assets, it observed 3I Atlas from a different angle, providing stereoscopic information that helped researchers build a three-dimensional understanding of the encounter geometry. How far was the comet from Mars at the moment each image was taken? From what direction was sunlight illuminating the coma? How did the appearance change over time as both Mars and the comet moved in their respective orbits? These weren't abstract questions. They were critical for interpreting the other data being collected, particularly the atmospheric measurements that would show whether cometary material actually reached Mars. Without precise knowledge of the geometry, those measurements would be ambiguous. With multiple images from different perspectives, the geometry could be nailed down with precision. But images in visible light only tell part of the story. Some of the most revealing data came from MAVEN's ultraviolet observations, which revealed details completely invisible to normal cameras. In ultraviolet wavelengths, comets light up with the glow of specific atoms and molecules being excited by solar radiation. Hydrogen, in particular, produces a characteristic ultraviolet emission that serves as a tracer for water, because water molecules in the comet's ice break apart when exposed to ultraviolet sunlight, releasing hydrogen atoms that glow in UV wavelengths. MAVEN's ultraviolet spectrograph wasn't just seeing reflected sunlight like a camera would, it was detecting the specific fingerprint of hydrogen emission, directly revealing the presence of water-derived material around 3I Atlas. And because MAVEN was designed to study Mars's atmosphere, it could distinguish between hydrogen that had been in the Martian exosphere for a long time and new hydrogen that had just arrived, potentially from the comet. The data showed something astonishing. During the hours around closest approach, MAVEN detected a measurable enhancement in hydrogen concentration in the regions of Mars's exosphere where the comet's path and the planet's atmosphere intersected. The enhancement was subtle, requiring careful analysis to distinguish from normal variations in atmospheric hydrogen, but it was there, statistically significant, reproducible across multiple measurement cycles, real. This wasn't just a close approach in geometrical terms, it was an actual physical interaction. Material from 3I Atlas, atoms that had originated in an interstellar environment, had reached Mars. The planet had been touched by a visitor from beyond, in a way that could be measured and quantified. The implications of this discovery would take months to fully unpack, but even in the immediate aftermath, researchers recognized they were looking at evidence of something extraordinary. Think about what that means. Every drop of water on Earth, every molecule in your body, every bit of hydrogen in our solar system came from one of two places. Either it was present in the primordial cloud of gas and dust that collapsed to form the Sun and planets, or it arrived later via comets and asteroids that had been wandering through our cosmic neighborhood for billions of years. But all of that material, regardless of when it arrived, shares a common heritage. It all formed from the same giant molecular cloud that gave birth to our Sun. It's all family in a sense. But the hydrogen atoms MAVEN detected around Mars during the 3I Atlas encounter weren't family. They were immigrants carrying passports stamped by a different star, perhaps a star that doesn't even exist anymore. They represented a brief contamination of our solar system's chemical inventory with material from a completely separate stellar lineage, and now some of those atoms were mixing with Mars's atmosphere, becoming part of the red planet's chemical story in a way that would be impossible to ever fully erase. The images and spectroscopic data also revealed details about 3I Atlas itself that had been impossible to determine before the close approach to Mars. The rate of hydrogen emission gave researchers a way to estimate how much water ice the comet was losing per second as it rounded the Sun, which in turn provided constraints on the comet's total size and mass. These weren't precise measurements. Comets are notoriously variable, and their activity can change rapidly as different patches of ice become exposed to sunlight or fall back into shadow as the nucleus rotates. But even rough estimates were valuable, because they helped place 3I Atlas in context with other interstellar objects. Was it typical or unusual? Did its behaviour match what we've seen from solar system comets, suggesting similar formation conditions? Or were there differences that hinted at exotic compositions or formation mechanisms? The Mars encounter provided data that no previous observations had captured, simply because no instrument had been positioned this perfectly to observe an interstellar object before. Among the most striking findings was evidence that 3I Atlas's composition included organic molecules, carbon-based compounds more complex than simple carbon monoxide or carbon dioxide. The spectroscopic signatures were subtle and required sophisticated analysis to extract from the noisy data, but multiple independent research teams reached the same conclusion. The comet carried organics, probably including complex hydrocarbons, and possibly even more intricate molecules that serve as precursors to the amino acids and nucleotides essential for life as we know it. This wasn't evidence of life, to be clear. Organic molecules form readily in interstellar space through non-biological chemistry, and finding them in a comet was expected rather than surprising, but it was still profound. Organic molecules from another star system had reached Mars. If even microscopic amounts of that material made it to the surface, then Mars now contains trace amounts of prebiotic chemistry from a completely different stellar environment. The building blocks of life are universal, it seems, and they travel between stars. Researchers also noted anomalies in the images that would fuel discussion for months afterward. Some observations showed brightness variations that didn't fit simple models of uniform outgassing from a rotating nucleus. The comet seemed to have active regions, patches that were particularly productive in releasing gas and dust, and those regions changed over time in ways that suggested complex processes on the surface or just below it. Perhaps pockets of especially volatile ice were being exposed as surface layers sublimated away. Perhaps subsurface cavities were occasionally venting built-up pressure, creating temporary jets that sprayed material into space. These kinds of features are common in solar system comets, and had been seen in previous interstellar visitors. But every comet is unique, and 3I Atlas was providing a masterclass in just how dynamic these ancient ice balls can be when the sun's heat starts unlocking their frozen contents. The human response to these images and revelations rippled outward from the tight community of researchers directly involved in the observations to a broader audience hungry for information about the encounter. Press releases went out. Conference presentations were scheduled. Papers began moving through the publication pipeline with unusual speed, as journal editors recognized that the scientific community wanted access to this data as soon as possible. News organizations picked up the story, translating the technical findings into language accessible to general audiences. Social media lit up with discussions, debates, and inevitably, speculation that went far beyond what the data could support. The images of 3I Atlas near Mars became iconic, reproduced in articles and documentaries, serving as visual shorthand for humanity's growing ability to study objects from beyond our solar system. For a few weeks, this encounter was front-page news, a reminder that space exploration can still capture public imagination when the story is compelling enough. But for the scientists who had worked so hard to make the observations possible, the public attention was almost beside the point. What mattered to them was the data itself, the permanent record now preserved in archives, ready to be analysed for years or decades to come. They understood that the immediate findings were just the beginning. Future researchers with better analytical tools, more sophisticated models, and the benefit of comparison with other interstellar objects yet to be discovered would return to this data again and again, extracting insights that the current generation might not even know to look for. The images and spectra captured during 3I Atlas's encounter with Mars were a gift to the future, a time capsule containing information about a moment when two separate cosmic histories briefly intersected, and humanity was there to witness and document it. The atmosphere of Mars is an underappreciated wonder. Most people, when they think about the red planet, focus on the surface, the towering volcanoes, the vast canyon systems, the polar ice caps that wax and wane with the seasons. But above all that geology, stretching from the dusty surface into the gradually thinning reaches of space, Mars possesses an atmosphere that tells stories about the planet's past, present, and relationship with the sun and solar wind. It's a thin atmosphere compared to Earth's, with surface pressure less than 1% of what we experience at sea level, but it's dynamic and complex, capable of generating global dust storms, supporting clouds of water ice and carbon dioxide, and responding to external influences in ways that reveal fundamental physics about how planetary atmospheres work. When 3I Atlas passed close to Mars, it was this atmosphere, particularly the uppermost layers where gas transitions into space, that became the stage for detecting the comet's influence. MAVEN's mission has always been about understanding Mars's upper atmosphere and exosphere, the region where atmospheric gases are so sparse that individual molecules can escape to space if they're moving fast enough. This is where Mars is actively losing its atmosphere, a slow bleeding that has been ongoing for billions of years and helps explain how the planet transformed from the warm, wet world that ancient river valleys suggest it once was into the cold, dry desert we see today. MAVEN's instruments measure the composition, temperature, and motion of gases in this tenuous environment, building a picture of how solar radiation and the solar wind, the stream of charged particles constantly flowing from the sun, interact with Mars's atmosphere. These measurements are routine, collected continuously as MAVEN orbits the planet, creating a baseline understanding of normal conditions. But normal conditions weren't what anyone expected when 3I Atlas passed by. The hydrogen enhancement that MAVEN detected wasn't just an interesting anomaly. It was a profound clue about the nature of the interaction between the comet and the planet. Hydrogen doesn't stick around in planetary atmospheres for long, especially not in the exosphere where the gravitational pull is weakest and molecules have the freedom to escape. When researchers saw hydrogen levels increase during the hours surrounding 3I Atlas's closest approach, they knew they were witnessing an injection of fresh material, atoms that had recently arrived and hadn't yet had time to disperse or escape. The timing was too perfect to be coincidental. The enhancement peaked right when theoretical models predicted 3I Atlas's gas and dust cloud would be overlapping with Mars's exosphere. Cause and effect couldn't be proven with absolute certainty. Science rarely offers that level of certainty. But the correlation was strong enough that the conclusion seemed inescapable. Cometary hydrogen had reached Mars. Where did that hydrogen come from? The answer takes us deep into the physics of how comets work. When a comet is far from the sun, it's essentially a frozen mixture of water ice, carbon dioxide ice, methane ice, ammonia ice, and various other volatile substances, all mixed together with rocky dust and organic compounds. The whole thing is locked in a deep freeze, inert and unchanging for potentially millions or billions of years. But as the comet approaches the sun and temperatures rise, those ices begin to sublimate, transitioning directly from solid to gas without passing through a liquid phase. Old water ice becomes water vapor, carbon dioxide ice becomes carbon dioxide gas. And as these gases escape from the nucleus, they carry away dust particles that had been frozen into the ice, creating the visible coma and tail that make comets spectacular when they're close enough to Earth to see clearly. But the story doesn't stop with water vapor. Ultraviolet radiation from the sun is energetic enough to break apart water molecules, a process called photodissociation. Each water molecule contains 2 hydrogen atoms and 1 oxygen atom, and when ultraviolet light hits that molecule with sufficient energy, it can rip the atoms apart. The hydrogen atoms, being extremely light, can be accelerated to high velocities by the energy of the breakup and by additional radiation pressure from sunlight. They form what's called a hydrogen corona around the comet, a vast invisible cloud of individual hydrogen atoms that can extend for enormous distances, much larger than the visible coma of dust and gas. This hydrogen corona is one of the primary ways scientists can track comets from afar. It emits characteristic ultraviolet light and can be detected by instruments like the one on MAVEN, even when the comet itself is too faint to see directly. When 3I Atlas passed close to Mars, its hydrogen corona enveloped portions of the planet's exosphere. You have to picture this at an atomic level to truly appreciate what happened. Individual hydrogen atoms, each one liberated from a water molecule that formed around a different star, travelling through space at speeds of many kilometres per second, suddenly finding themselves in the gravitational and electromagnetic environment around Mars. Some of those atoms would have passed right through the exosphere without interacting with anything. Space is mostly empty after all, and even in a relatively dense region like a planetary exosphere, collisions between atoms are rare. But some atoms would have collided with atmospheric molecules, exchanging energy and momentum, becoming temporarily captured in orbits around Mars before eventually escaping or being absorbed. And some would have been detected by MAVEN's instruments, adding their signal to the ultraviolet glow of Mars's own atmospheric hydrogen, creating the enhancement that told researchers the interaction had occurred. The measurements weren't limited to hydrogen. MAVEN's instruments can detect multiple species of atoms and molecules, and careful analysis of the data revealed subtle signatures of other cometary material as well. Oxygen, liberated from water molecules just like hydrogen, but heavier and therefore moving more slowly and staying closer to the comet, showed a measurable increase during the encounter period. Carbon, likely originating from carbon dioxide and organic molecules in the comet, also appeared in slightly elevated concentrations. These detections were more challenging to confirm than the hydrogen signal, because the natural variability in Mars's atmosphere is larger for these heavier species, making it harder to distinguish a small enhancement caused by cometary material from normal fluctuations. But multiple independent analyses using different techniques reached similar conclusions. The statistical evidence supported the interpretation that 3I Atlas had contributed measurable amounts of multiple elements to Mars's upper atmosphere. What happened to that cometary material after it arrived? This is where the story becomes more speculative, because the fate of individual atoms in a planetary atmosphere depends on many factors that are difficult to track. Some of the hydrogen, being so light and energetic, almost certainly escaped Mars entirely, reaching velocities high enough to overcome the planet's gravity and joining the stream of particles constantly being stripped from Mars by the solar wind. Those atoms are gone now, dispersed into interplanetary space, eventually destined to be swept up by the sun, or incorporated into dust grains, or simply becoming part of the tenuous background of atoms that fill the solar system. But some of the heavier atoms, oxygen, carbon, and perhaps traces of other elements, might have settled into lower layers of the atmosphere, mixing with the native Martian gases and becoming, for all practical purposes, indistinguishable from the planet's own atmospheric inventory. There's something both beautiful and melancholy about that possibility. If cometary atoms did incorporate into Mars's atmosphere, then the planet now carries a permanent, if unmeasurable, trace of 3I Atlas. Every future measurement of Martian atmospheric composition includes those atoms. Every future spacecraft that samples the Martian atmosphere is, in an infinitesimal way, sampling material from beyond our solar system. The effect is too small to ever detect directly. The number of atoms involved is minuscule compared to the total mass of Mars's atmosphere, but philosophically, scientifically, it represents a permanent change. Mars is no longer composed purely of material born in our solar system. It has been contaminated, in the most neutral sense of that word, with matter from elsewhere. The boundary between here and there, between our cosmic neighbourhood and the wider galaxy, has been shown to be permeable in a way that most people never think about. The chemical signatures also provided insights into the composition of 3I Atlas itself, complementing what had been learned from visible light observations and spectroscopy. The ratios of different elements, how much hydrogen relative to oxygen, how much carbon relative to nitrogen, gave clues about the original ice composition of the comet and therefore about the conditions in the stellar environment where it formed. Was 3I Atlas similar in composition to solar system comets, suggesting that the chemistry of star formation and planetary system formation is universal? Or were there subtle differences that might point to variations in stellar nursery conditions across the galaxy? The data wasn't conclusive. Too many uncertainties existed in how to interpret the measurements, but it added valuable data points to a picture that scientists are still piecing together about how diverse or uniform planetary system formation might be across different stellar environments. One of the most intriguing aspects of MAVEN's observations was the time evolution of the signals. The hydrogen enhancement didn't appear instantly and then disappear. It built gradually over several hours, peaked around the time of closest approach, and then declined slowly as 3I Atlas moved away and the densest part of its coma and corona swept past Mars. This temporal structure provided information about the three-dimensional shape of the comet's gas cloud and how it was oriented relative to Mars's orbit. By tracking how the signal changed minute by minute, researchers could reconstruct the geometry of the encounter with greater precision than position measurements alone would allow. It was like watching the shadow of a passing object and using the shadow's shape and motion to figure out the three-dimensional form of the object itself, a technique astronomers have used for centuries but rarely with such immediate as dramatic application. The discovery also had implications for understanding similar encounters that might have happened throughout Mars's history. Comets from within our solar system occasionally pass near Mars, not as frequently as they approach Earth or Jupiter, but it happens often enough over geological timescales that Mars has likely been exposed to cometary material many times throughout its 4 billion-year history. But interstellar comets are far rarer. Based on current estimates of how frequently these objects pass through the inner solar system, encounters like the one with 3I Atlas might occur only once every few million years. Over Mars's entire history, there might have been thousands of such encounters, each one depositing trace amounts of interstellar material into the Martian environment. Could that material have played any role in Mars's history? Could interstellar organics delivered by ancient encounters have contributed to the chemistry that might have supported life when Mars was young and wet? These questions venture into speculation, but they're grounded in the concrete evidence that such material can reach Mars and that the chemistry of life's building blocks is universal. Looking at the data from MAVEN and the other spacecraft, what emerges is a portrait of an encounter that was simultaneously subtle and profound. Subtle because the actual changes to Mars were minuscule, a tiny enhancement in atmospheric hydrogen, a brief injection of atoms that quickly dispersed or escaped. From Mars's perspective, if the planet could have a perspective, the passing of 3I Atlas might have been barely noticeable, a whisper rather than a shout. But profound because that whisper carried information from another stellar realm, because it demonstrated that the boundary between solar systems is not absolute, and because it gave humanity a detailed case study in how worlds can be touched by travellers from the cosmic deep. The signatures in the Martian skies were faint, but they were real, and they told a story that researchers will be analysing and learning from for decades to come. The question haunts discussions in observatories and planetary science conferences, debated with the kind of careful intensity that characterises scientific discourse when the answer matters. Did 3I Atlas actually change Mars in any lasting way, or was the encounter merely a fleeting interaction that left no permanent mark? On the surface, the question might seem to have an obvious answer. A small comet passes briefly near a planet, sheds some gas and dust, and then continues on its way. How much change could possibly result from such a brief encounter? But the deeper you dig into the question, the more complex it becomes, because change can be measured in many ways, and permanence is a relative concept when you're discussing planetary timescales. Start with the most conservative position, the one favoured by researchers who prioritise caution over speculation. From this perspective, 3I Atlas caused no meaningful permanent change to Mars. Yes, the MAVEN data showed atmospheric enhancements during the encounter. Yes, material from the comet likely reached Mars's exosphere, and possibly even lower atmospheric layers. But the total mass involved was infinitesimal compared to Mars itself, or even compared to Mars's atmosphere. Whatever atoms or molecules arrived from the comet would have dispersed rapidly, mixing with the vastly larger inventory of native Martian gases, or escaping into space, leaving behind no signature that could ever be detected again. In this view, the encounter was scientifically valuable as an observational opportunity, but calling Mars changed by it would be like claiming a lake has been fundamentally altered because a single raindrop fell into it. This conservative position is intellectually defensible and probably technically correct in the narrow sense of measurable physical changes, but it also misses something important about how we think about planetary science and cosmic events. Consider how we talk about Earth and the events that have shaped it. We say Earth was changed by the asteroid impact that ended the age of dinosaurs 66 million years ago, and that statement is obviously true. The impact caused extinctions, climate shifts, and ecological transformations that reshaped the planet's biosphere. But we also say Earth was changed by less dramatic events. The arrival of free oxygen in the atmosphere billions of years ago, the gradual shifting of continents, even the human-caused increase in greenhouse gases over the past century. Change comes in many scales, and significance isn't always proportional to mass or energy. So what kind of changes might 3I Atlas have caused, and how do we evaluate their significance? The most direct and least controversial is the atmospheric injection we've already discussed. Material from the comet entered Mars's upper atmosphere. Some of it might have descended to lower altitudes or even reached the surface, though the quantities involved would be unmeasurably small. But here's where things get interesting from a philosophical or historical perspective. If even a single atom from 3I Atlas landed on Mars and became incorporated into the surface soil or rock, then Mars is now compositionally different than it was before the encounter. Not measurably different. The change is far too small for any instrument to detect, but actually physically different in a way that is in principle permanent. That atom won't simply disappear. Barring some unlikely sequence of events that liberates it back into space, it's now part of Mars, a permanent addition to the planet's inventory of matter. Does that matter? In practical terms, no. In symbolic or philosophical terms, maybe yes. It represents a physical connection between Mars and the interstellar medium, a tangible proof that planetary systems aren't closed boxes, but rather open systems that exchange material with the broader galaxy. We've known this abstractly for a long time. Meteorites bring interstellar grains to Earth. Solar wind carries material from other stars into our solar system. Cosmic rays from distant supernovae constantly bombard all the planets. But there's something particularly vivid about the 3I Atlas encounter. Because it was observed, documented and confirmed in real time. We watched it happen, we measured the exchange of material. We can point to specific data showing that atoms from a comet born around another star reached Mars and interacted with its atmosphere. That transforms an abstract principle into concrete reality. Some researchers have speculated about more dramatic effects, though these ideas remain firmly in the realm of hypothesis rather than demonstrated fact. Could the encounter have triggered changes in Mars's upper atmosphere that persisted beyond the immediate period when cometary material was present? Atmospheres are dynamic systems, capable of feedback loops and nonlinear responses to perturbations. A small injection of energy or material in the right place at the right time can sometimes trigger larger-scale phenomena. We see this on Earth with weather systems. Tiny initial differences can, through chaotic dynamics, lead to dramatically different outcomes days or weeks later. Could something similar have happened in Mars's tenuous upper atmosphere? The honest answer is that we don't know, and we might never know, because detecting such effects would require continuous monitoring with instruments that might not have been looking for the right signals at the right times. There's also the question of electromagnetic effects. Mars has only a weak, patchy magnetic field, nothing like Earth's global magnetic envelope, but it does have localized magnetic anomalies, particularly in the ancient cratered highlands of the southern hemisphere. These magnetic patches interact with the solar wind and with charged particles in Mars's ionosphere in complex ways. When 3I Atlas passed close to Mars, it would have been shedding not just neutral gas and dust, but also ions, electrically charged atoms and molecules created by ultraviolet radiation from the sun. Could those ions have interacted with Mars's magnetic patches or ionosphere in ways that created transient or even semi-permanent changes in the electromagnetic environment around the planet? Again, we don't know. The necessary measurements would have required spacecraft in the right place at the right time with instruments specifically designed to detect subtle electromagnetic phenomena. Some data exists, but it hasn't been analysed with this question in mind, and it's unclear whether it ever will be. Research funding is finite, and scientists have to prioritise which questions to pursue. The speculation that generates the most public attention, though it's the least supported by actual evidence, involves potential biological or chemical effects. We know that 3I Atlas likely carried organic molecules. That's a reasonable inference from spectroscopic data and from general principles about cometary composition. We know that some cometary material probably reached Mars's atmosphere and possibly its surface. Could any of those organic molecules have survived the journey and deposition to become incorporated into Martian soil? And if so, could they have any relevance to the question of whether Mars has ever hosted life, or could potentially host life in the future? The answers are, respectively, Maybe extremely unlikely, and almost certainly not, but the questions themselves illustrate why the 3i Atlas encounter captured public imagination beyond what you might expect for a purely astronomical event. Let's be clear about what the evidence does and doesn't support. There is zero evidence that 3i Atlas deposited biologically significant amounts of organic material on Mars. Zero evidence that any such material could survive the harsh conditions of Mars's surface environment long enough to matter. Zero evidence that contemporary Martian conditions could support any kind of biology anyway, regardless of what organic molecules might be present. The organic chemistry relevant to life requires liquid water, energy sources, and a suite of specific conditions that Mars simply doesn't have, at least not at its surface. Anyone suggesting that 3i Atlas somehow seeded Mars with life, or contributed meaningfully to the potential for future life, is engaging in speculation so extreme that it crosses the line into baseless conjecture. It makes for compelling storytelling but bad science. And yet, even after acknowledging all of that, there's a kernel of something worth thinking about in the question of how interstellar organics might affect planetary environments over very long timescales. Mars has been accumulating material from space throughout its entire existence. Meteorites, cosmic dust, solar wind particles, and yes, probably occasional interstellar visitors like 3i Atlas. Over 4 billion years, that accumulated material adds up to a non-trivial mass, and some fraction of it includes organic molecules. Does that matter for Mars's long-term chemical evolution? Does it contribute to the inventory of building blocks that would be available if Mars's environmental conditions ever became more hospitable? These are legitimate scientific questions, even if the contribution from any single encounter like the one with 3i Atlas is vanishingly small. What about changes to 3i Atlas itself? The encounter was mutual. Not only did Mars experience the close passage of an interstellar comet, but the comet experienced the close passage of a planet. Mars's gravity, though small compared to Jupiter's or even Earth's, would have subtly altered 3i Atlas's trajectory. The deflection would be tiny, perhaps changing the comet's velocity by mere meters per second. But that tiny change becomes significant when extrapolated over the millions of years that 3i Atlas will spend travelling through interstellar space. Where the comet ends up, what star system it might approach next, whether it will ever encounter another planet again, all of that could have been changed by the Mars encounter. In that sense, Mars definitely changed 3i Atlas, and the change is permanent and consequential. The two objects exchanged gravitational influence, and both emerged on slightly different trajectories through space and time than they would have followed otherwise. There's a poetic symmetry to that. Mars and 3i Atlas both changed each other, each leaving a mark that will persist even after the encounter has faded into history. The changes might be subtle, unmeasurable, or only meaningful when considered over timescales that dwarf human civilization, but they're real, and they remind us that nothing in the universe is truly isolated. Every object influences and is influenced by everything around it, through gravity, through electromagnetic forces, through the simple physical fact of occupying space and exchanging radiation and matter with the environment. Mars experienced 3i Atlas. 3i Atlas experienced Mars, and the universe is different, in ways large and small, because that encounter happened. So was Mars changed forever? The answer depends on how you define changed and what timescales you care about. If you mean measurable, detectable changes in Mars's composition, atmosphere, or geology, then probably not. The effects were too small to persist in any observable way. But if you mean whether the encounter left any permanent mark, however subtle, whether it altered Mars's trajectory through cosmic history in even the tiniest way, then yes, absolutely. Mars is different because 3i Atlas passed by. The difference might be unmeasurable, but it's real. And for those of us fascinated by the question of how worlds influence each other across the vast distances of space, that's enough to matter. The encounter between 3i Atlas and Mars served as something unexpected and valuable to the planetary defence community, a natural experiment in detection, tracking and rapid response that tested systems and protocols originally designed to protect Earth from potentially hazardous asteroids and comets. Planetary defence, as a field, emerged from the recognition that impacts from space objects are not just ancient history, but ongoing threats. The dinosaurs learned this lesson 66 million years ago. More recently, the Chelyabinsk meteor that exploded over Russia in 2013 provided a stark reminder that even relatively small objects can cause significant damage if they strike populated areas. Since then, space agencies around the world have invested in survey programs to find and track near-Earth objects, develop techniques to predict their trajectories, and even test methods for deflecting dangerous asteroids before they hit. Interstellar objects like 3I Atlas add a fascinating wrinkle to planetary defense thinking. They're not threats in the traditional sense. Their trajectories carry them through the solar system too quickly to be captured into Earth-crossing orbits, and their hyperbolic paths mean they won't be returning on regular predictable schedules like asteroids or short-period comets do. But they're challenging from a detection and tracking perspective, because they can arrive from any direction, not just from the ecliptic plane where most solar system objects orbit. And they move fast, meaning that the window between detection and closest approach to Earth or other planets can be measured in months rather than years or decades. The 3I Atlas encounter with Mars provided a case study in how well current systems can handle that challenge. The answer, it turns out, is pretty well, though not without room for improvement. 3I Atlas was discovered with sufficient advance notice that trajectory predictions were refined well before it approached Mars. Multiple observatories contributed tracking data, allowing researchers to calculate the orbit with high precision and predict the closest approach, distance, and time accurately. When the time came, spacecraft and telescopes were positioned and ready, demonstrating that the coordination and communication systems that underpin modern astronomy can respond effectively to rapidly developing situations. This is no small achievement. The astronomical community is not a single monolithic organization. It's a loosely coordinated network of observatories, space agencies, universities, and individual researchers operating under different funding sources, national priorities, and institutional constraints. That such a network can mobilize quickly and effectively when a unique opportunity arises speaks well of the maturity of the field. But the experience also highlighted limitations and areas where improvements are needed. The time between discovering an interstellar object and having it pass through the inner solar system is short, typically just months from discovery to closest approach to the Sun. That doesn't leave much time for launching new spacecraft or deploying specialized instruments if what you have in orbit or on the ground isn't already adequate. Luck played a role in the 3I Atlas observations. If there had been no spacecraft orbiting Mars, if MAVEN hadn't been designed with instruments capable of detecting atmospheric changes, if the government shutdown had affected operations more severely, the quality and completeness of data would have been compromised. Future encounters might not be so fortunate. The solution is to ensure that sufficient observational assets are always available, always maintained, and always ready to be retasked quickly. That requires sustained funding and institutional commitment, which are always challenging in an era of competing priorities. The 3I Atlas encounter also spurred discussions about whether interstellar objects could ever pose a direct threat to Earth. The consensus among experts is that the risk is extremely low but not zero. Interstellar objects are rare. Most that pass through the solar system remain far from Earth. The chances of one happening to be on a collision course with our planet are astronomically small. But small chances are not the same as no chance. And over long enough timescales, even improbable events eventually occur. If an interstellar comet or asteroid were headed for Earth, could we do anything about it? The techniques being developed for deflecting solar system asteroids, kinetic impactors, gravity tractors, even nuclear explosions to vaporize or push objects off course, might work, but the timescales would be much tighter. Deflecting an asteroid that's been tracked for years and whose orbit is well understood is one thing. Deflecting an interstellar object that was only discovered a few months before potential impact is a much more challenging proposition. Fortunately, this remains a hypothetical concern rather than an immediate one. The real value of studying interstellar objects isn't for planetary defense, it's for the pure science. Every visitor from beyond our solar system is an opportunity to study material that formed under different conditions, to test whether our theories about planet formation and stellar chemistry are universal or parochial, to glimpse the diversity of environments that exist across the galaxy. The 3I Atlas encounter demonstrated that when such opportunities arise, humanity has the technological capability and organizational capacity to respond effectively. That's reassuring not just for planetary defense, but for the broader project of understanding our place in the universe. the trajectory data collected during the Mars encounter contributed to a refined understanding of how interstellar objects move through gravitational fields. When 3I Atlas entered the solar system, its trajectory was determined primarily by its initial velocity and direction from interstellar space, plus the gravitational influence of the Sun. But as it passed close to Mars, the planet's gravity tugged on the comet, changing its trajectory slightly. Measuring that deflection with precision provided data that can be used to improve models of orbital mechanics, particularly the subtle gravitational interactions that occur during close approaches. These improvements might seem academic, but they have practical applications. Accurate trajectory prediction is essential for planetary defense, for planning spacecraft missions, and for understanding the long-term evolution of the solar system. Looking forward, the 3I Atlas experience informed planning for future interstellar object encounters. Astronomers now have a better sense of what kinds of observations are most valuable, what instruments are best suited for different types of measurements, and how to coordinate international efforts efficiently. The next interstellar visitor, and there will be more eventually, will benefit from lessons learned during the 3I Atlas encounter. Perhaps next time, there will be a dedicated interstellar object rapid response program, with funding already in place and protocols already established for quickly organizing observing campaigns. Perhaps next time, there will be spacecraft already in position, or capable of being retargeted quickly enough to conduct close-up studies. Perhaps next time the data will be even richer and more comprehensive, advancing our understanding of these cosmic travelers even further. There's also renewed interest in the possibility of detecting interstellar objects earlier, when they're still far from the Sun, and moving slowly enough that launching a spacecraft to intercept them might be feasible. Current detection methods rely primarily on discovering these objects after they've brightened due to solar heating, which typically doesn't happen until they're well into the inner solar system. But if we could detect them earlier, using infrared surveys for instance, which can spot the faint heat signature of distant objects, we'd have more time to plan detailed studies or even missions. Several proposed survey projects aim to do exactly that, scanning the skies for faint, fast-moving objects that might be interstellar visitors. If funded and implemented, these surveys could dramatically increase the number of known interstellar objects and provide much earlier warning of interesting encounters like the one between 3I Atlas and Mars. The encounter also reinforced the importance of maintaining and supporting existing spacecraft and ground-based assets. MAVEN is more than a decade old now, having launched in 2013. It wasn't designed specifically to study interstellar comets. It couldn't have been, since the first confirmed interstellar object wasn't discovered until 2017. But because MAVEN was there, operational, and equipped with capable instruments, it was able to contribute essential data to understanding the 3I Atlas encounter. This is a pattern that repeats throughout the history of space exploration. Missions designed for one purpose end up making unexpected discoveries because they are in the right place at the right time. The lesson is that long-lived missions are valuable not just for their primary objectives, but for the flexibility they provide to respond to unexpected opportunities. Keeping spacecraft healthy and operational for as long as possible maximizes the return on the enormous investment required to launch and operate them. There's a strategic dimension to all of this that goes beyond science. Demonstrating capability in detecting, tracking, and studying objects that move through space on unpredictable trajectories has implications for national security and international cooperation. The same technologies and organizational systems used to track asteroids or interstellar comets could potentially be applied to tracking artificial objects, satellites, debris, or even threats. The 3I Atlas encounter, by providing a real-world test case for rapid international scientific coordination, demonstrated that when motivations align around a common scientific goal, nations can work together effectively despite political differences. That's a valuable precedent, and it builds relationships and trust that might prove useful in other contexts. Ultimately, what the planetary defense community took away from the 3I Atlas encounter was a mixture of confidence and humility. Confidence that current systems work reasonably well for detecting and characterizing objects that approach Earth or other planets. Humility about how much remains unknown and how much more capability is needed to fully understand and protect against cosmic threats. The encounter was a success story, a demonstration that humanity is beginning to mature into a species capable of monitoring its cosmic environment and responding thoughtfully to what it finds there. but it was also a reminder that we're still at the beginning of that journey, and that continued investment, innovation, and international cooperation will be essential for facing whatever challenges or opportunities the universe sends our way next. Within hours of the first news reports about 3i Atlas's close approach to Mars, the internet began generating alternative narratives, many of them divorced from the careful scientific discourse that characterized the actual observations. Forums and social media platforms lit up with speculation that ranged from merely unlikely to outright absurd. Some claimed the comet wasn't natural at all, but rather an alien probe deliberately targeting Mars. Others suggested that the timing of the government shutdown wasn't coincidental, that it was orchestrated to hide information about the encounter from the public. Still others wove elaborate theories involving secret NASA discoveries, suppressed data about changes to Mars, and conspiracies reaching into the highest levels of government and international space agencies. None of these ideas had any basis in evidence, but that didn't prevent them from spreading rapidly through communities hungry for mystery and suspicious of official narratives. Why does this happen? The question is worth exploring because it reveals something fundamental about human psychology and how we respond to events we don't fully understand. Scientific discoveries, especially in astronomy, often challenge our intuitions about how the universe works. They present us with events or phenomena that seem improbable, extraordinary, or difficult to grasp emotionally even when the intellectual understanding is clear. An interstellar object, something born around another star travelling through the darkness between stellar systems for who knows how long. Passing close to Mars feels like it should mean something beyond just orbital mechanics and atmospheric chemistry. It feels like it should have significance, purpose, intention. Our brains evolved to find patterns and assign causation, especially for events that seem too remarkable to be random. When science provides explanations that feel mundane compared to the grandeur of the event, some people reject those explanations in favour of more dramatic narratives. The alien probe theory is particularly instructive because it follows a pattern seen repeatedly throughout the history of space exploration. Whenever something unusual or unexplained is observed in space, someone will suggest it might be evidence of extraterrestrial intelligence. The infamous case of Oumuamua, the first confirmed interstellar object discovered in 2017, generated widespread speculation that it was an alien artifact, fueled in part by its unusual shape and the slight, unexplained acceleration it exhibited as it left the solar system. Serious scientists, including some respected astronomers, publicly entertained the possibility even though the evidence supporting natural explanations was far stronger. With 3i Atlas, similar dynamics played out. The comet's origin beyond our solar system, its apparently deliberate trajectory toward Mars, and the coincidental timing with political disruptions on Earth all combined to create a narrative framework that felt to some more like a designed event than a random encounter. But let's be absolutely clear. There is zero credible evidence that 3i Atlas is anything other than a natural comet. Its behaviour matches what we expect from icy bodies heated by solar radiation. Its spectrum shows the chemical signatures of water ice, carbon dioxide and organic molecules, exactly what comets should contain. Its trajectory follows the laws of orbital mechanics precisely, with no anomalous accelerations or course changes that might suggest propulsion or guidance. The idea that it's an alien probe requires us to discard all of this evidence and replace it with speculation based on what? The fact that it passed near Mars. Countless natural objects have passed near planets throughout the history of the solar system. The fact that it's from interstellar space? That makes it rare and interesting, but rarity alone isn't evidence of artificial origin. The alien probe hypothesis is unfalsifiable speculation that explains nothing and predicts nothing. It's storytelling masquerading as investigation. The government shutdown conspiracy theories are similarly baseless, but reveal interesting assumptions about how science and government interact. The shutdown did complicate NASA operations during the 3i Atlas encounter, that much is true, but the complications were logistical and bureaucratic, not secretive. Scientists discussed them openly in interviews and public statements. Data from the encounter was shared promptly with the international scientific community, and eventually made publicly available through standard archival processes. If there were a conspiracy to hide information, it failed spectacularly, because we have extensive documentation of what was observed, who observed it, and what the data shows. Moreover, the conspiracy theory requires believing that multiple space agencies across multiple countries all agreed to participate in a cover-up, coordinating their public statements and suppressed findings despite having no obvious motivation to do so, and operating under entirely different governmental and cultural systems. The logistics of such a conspiracy would be more impressive than anything 3i Atlas actually did. Yet these narratives persist and even thrive in certain communities. Why? Part of the answer is cultural. We live in an era of declining trust in institutions, where official statements from government agencies or scientific organizations are often met with skepticism or outright disbelief. When people don't trust the messengers, they're less likely to accept the message, no matter how well supported by evidence. Another part of the answer is psychological. Conspiracy theories provide a sense of hidden knowledge, of being among the enlightened few who see through official lies to the secret truth underneath. That feeling can be intoxicating, creating social bonds among believers and providing a sense of meaning and purpose that mundane reality sometimes lacks. And finally, there's the simple fact that dramatic conspiratorial narratives are more entertaining than careful scientific explanations. They're better stories, even if they're false stories. Does any of this matter? One perspective says no, let people believe what they want, as long as it doesn't directly harm anyone. The truth is available for those who seek it, and those who prefer fantasy to reality are exercising their freedom to be wrong. But another perspective says yes, it matters quite a bit. Scientific literacy and trust in evidence-based reasoning are essential for a functioning society, particularly in an era when complex challenges like climate change, pandemic response, and resource management require collective action based on accurate understanding of the world. When large segments of the population distrust scientific institutions or prefer conspiracy theories to evidence, it becomes harder to address these challenges effectively. The 3i Atlas encounter, in isolation, isn't that important. Whether people believe accurate information about a comet's close approach to Mars doesn't affect their daily lives. But the pattern of thinking that leads people to reject scientific consensus about 3i Atlas is the same pattern that leads them to reject consensus about vaccines, climate science, or any other area where evidence conflicts with preferred beliefs. What's the appropriate response? From the scientific community, it requires better communication, explaining not just what was observed, but how we know what we know, why alternative explanations don't fit the evidence, and what uncertainties remain. Good science communication acknowledges doubt and complexity, while still conveying the strength of established conclusions. It respects the audience enough to show the reasoning process, not just the final answer. It also requires humility. Scientists don't know everything, and sometimes confident predictions turn out to be wrong. Acknowledging this doesn't undermine science, it strengthens it by showing that science is self-correcting, that it updates beliefs when new evidence emerges. From the public, it requires a willingness to sit with uncertainty and ambiguity, to accept that not everything has a clear, simple explanation, and that sometimes the truthful answer is, we're not sure yet. It requires distinguishing between healthy skepticism, questioning claims and demanding evidence, and cynical dismissal of all expert consensus. It requires recognizing that while authorities and institutions sometimes make mistakes or even lie, the solution isn't to assume everything they say is false, but rather to develop the tools to evaluate evidence independently. The truth about 3i Atlas and its encounter with Mars is available. It's in the published papers, the archived data, the public statements from multiple independent research groups. Anyone with the time and background can verify it. That's how science works, not through appeals to authority, but through transparent evidence that anyone can examine. There's also room for wonder and speculation, as long as it's clearly labelled as such. Asking what-if questions, imagining alternative possibilities, exploring ideas that go beyond current evidence, these are all valuable cognitive exercises. Science fiction has long played this role, using space exploration and cosmic mysteries as launching points for stories that explore human nature, ethics, and possibility. The problem arises when speculation gets presented as fact, when what if becomes, this is what's really happening, and when entertainment narratives displace evidential reasoning. We can enjoy imagining that 3i Atlas might be an alien probe, while simultaneously understanding that all actual evidence points to it being a natural comet. The two modes of thinking imaginative speculation, and evidence-based analysis serve different purposes and shouldn't be confused with each other. The human need for answers, for meaning, for stories that make sense of the universe is universal and valuable. It's what drives both science and art, both investigation and creativity. The challenge is channeling that need in directions that illuminate rather than obscure, that expand understanding rather than replacing it with comforting fictions. The 3i Atlas encounter offers a perfect case study because the truth is actually quite remarkable. An object from beyond our solar system, carrying chemical signatures from a different stellar environment, passed close enough to Mars that we could study it in detail and detect its influence on the planet's atmosphere. That's an extraordinary story, and it's real. It connects us to the broader cosmos in concrete ways. It demonstrates that the universe occasionally arranges events so unlikely that they feel designed even when they're not. It shows that patient observation and careful analysis can reveal wonders that no conspiracy theory or alien probe hypothesis could improve upon. Sometimes reality is strange enough that we don't need to invent alternatives. There's a melancholy to watching something precious disappear, knowing you'll never see it again. The 3i Atlas encounter with Mars lasted only hours at its most intense, and even the extended observation period when the comet was close enough for detailed study spanned just days to weeks. Then came the inevitable departure, 3i Atlas continuing on its hyperbolic trajectory, moving outward through the solar system, past the orbit of Jupiter, past Saturn, eventually reaching the outer regions where the sun's influence weakens and the vast darkness of interstellar space begins. Telescopes tracked the comet as long as they could, watching it fade as distance increased and solar heating decreased, watching the coma shrink as outgassing slowed, watching it transform from an active object bright enough to study in detail back into the dormant ice ball it had been during its long journey through the galactic void. The final observations carried their own significance. Every additional day of tracking refined the trajectory calculations, improving our understanding of where 3i Atlas came from and where it's going. The comet's path through our solar system bent its trajectory slightly. Not just the Mars encounter, but the combined gravitational influence of all the mass it passed near, with the sun's gravity dominating but every planet contributing its small tug. By the time 3i Atlas exits the sun's sphere of influence and returns to truly interstellar space, it will be travelling in a slightly different direction than it was when it arrived. Where will that new trajectory take it? The calculations show it heading roughly toward the constellation of Cygnus, but toward is a loose term when discussing interstellar distances. The nearest stars in that direction are light years away, and 3i Atlas is travelling at a few dozen kilometres per second, fast by solar system standards, but glacially slow for covering interstellar distances. It will take tens of thousands of years before the comet approaches another star system, and even then, it's likely to pass through the outer reaches without coming anywhere near planets or moons. There's something profound in that timeline. 3i Atlas's visit to our solar system, this encounter that captivated astronomers and generated so much data and discussion, represents just a brief moment in a journey that has likely spanned millions of years and will continue for millions more. The comet exists on timescales that make human civilization look like a flicker. It was ancient before humans evolved, and it will still be travelling through space long after our species is gone. Assuming we don't manage to escape our own planet and spread throughout the galaxy ourselves, the comet is a time traveller of sorts, carrying material and memories from stellar environments that might have changed or ceased to exist since the comet began its journey. When 3i Atlas eventually encounters another planetary system, if it ever does, what will it carry with it from our solar system? A few molecules knocked loose during the Mars encounter, a subtle change in rotation or surface structure from solar heating, traces of dust collected while passing through the zodiacal cloud. The exchange is mutual but asymmetric. Our solar system will likely forget. 3i Atlas, far faster than the comet, will forget us, if a chunk of ice and rock can be said to remember anything. The global response to the comet's departure was muted compared to the excitement during the encounter, but for those who'd been tracking it since discovery, the moment carried emotional weight. Astronomers posted final images and spectra to social media, often with captions reflecting on what the observation campaign had meant to them personally and professionally. Some researchers who had devoted months to studying 3I Atlas expressed a kind of affectionate farewell, acknowledging the strangeness of feeling attachment to a cosmic object, but unable to deny the connection they felt. When you spend hundreds of hours analysing data from something, when you come to understand its behaviour and characteristics in intimate detail, when you coordinate with colleagues around the world in a shared effort to extract every possible piece of information from fleeting observations, a bond forms. Not a bond of reciprocal awareness, the comet is utterly indifferent to human attention, but a bond nonetheless rooted in the very human tendency to find meaning and relationship in the objects of our focus and care. Amateur astronomers contributed to the farewell observations, tracking 3 Atlas until it became too faint for backyard telescopes to detect. Online communities shared images and encouraged each other to capture last looks before the opportunity vanished. Some observers created time-lapse sequences showing the comet's motion against background stars over successive nights, visual records of its steady departure from the inner solar system. These contributions weren't scientifically essential. Professional observatories had the sensitivity and precision to track the comet much longer and with greater accuracy. But they mattered for other reasons. They represented public engagement with a cosmic event, ordinary people taking the time to turn telescopes skyward and witness something rare, to participate however modestly in documenting a moment of interstellar visitation. That kind of engagement is its own form of value, independent of the scientific return. Educational institutions incorporated the 3I Atlas encounter into curricula, using it as a real-world case study for teaching orbital mechanics, spectroscopy, and planetary science. Students calculated the comet's trajectory themselves, using publicly available data and the same equations that professional astronomers employed. Some schools organised observation nights, inviting families to view the comet through telescopes and hear presentations about why it mattered. Teachers used the encounter to illustrate how science works, not as a collection of facts handed down from authorities, but as a process of observation, analysis, debate, and gradual convergence on understanding. The comet became a teaching tool, its value extending beyond the immediate scientific data to impact how a generation of students learn to think about the universe and their place within it. The media cycle moved on, as media cycles do. Within weeks of the Mars encounter, other stories dominated headlines, and 3I Atlas faded from public consciousness. For most people, the comet's departure passed unnoticed, its brief moment of fame eclipsed by newer events and concerns. This is natural and inevitable. Attention is finite, and the world constantly generates new phenomena demanding notice. But for the research community, the real work was just accelerating. The observations were complete, but analysis would continue for years. Papers would be published, conferences would feature presentations dissecting every aspect of the encounter, graduate students would write dissertations based on the data. The comet might be departing physically, but its scientific presence would linger, influencing planetary science and cometary studies for the foreseeable future. What did the encounter ultimately reveal? A partial answer emerges from the published research, but the full answer remains incomplete and perhaps always will. We learned about 3I Atlas's composition, confirming it contained water ice, organic molecules, and rocky dust in proportions somewhat similar to solar system comets, but with intriguing differences that hinted at its interstellar origin. We learned about how interstellar objects can interact with planetary atmospheres, providing a rare case study in cross-contamination between a planet and cometary material from another stellar system. We learned about the trajectories these objects follow and how planetary encounters alter their paths. We learned about our own capabilities, what we can and cannot detect, how quickly we can mobilize observational resources, how effectively international cooperation can function when properly motivated. But we also learned about the limits of knowledge. Many questions remained unanswered, or only partially answered. What star system did 3I Atlas originate from? We have rough trajectories pointing toward a general region of the galaxy, but narrowing it down to a specific star, if that's even possible, given how stellar motions have shifted over the millions of years the comet has been travelling, remains beyond current capabilities. How long has it been travelling? Age estimates based on surface weathering and ice loss are uncertain by orders of magnitude. Will it ever encounter another planet around another star? Or will it wander the galaxy indefinitely, a perpetual nomad never quite finding another home? The answer is unknowable without tracking it far longer than human civilization is likely to exist. There's beauty in that incompleteness, in the recognition that some questions extend beyond our ability to answer. Science is often portrayed as a relentless march toward complete understanding, but a more accurate description might be a gradual expansion of knowledge accompanied by the discovery of ever more refined questions. The 3i Atlas encounter answered some questions definitively, while raising others that might occupy researchers for decades. That's how science progresses, not in straight lines toward final truth, but in branching paths of investigation, where each answer illuminates new mysteries. As 3i Atlas receded into the outer solar system, crossing the orbit of Saturn and heading toward the heliopause, the boundary where the sun's influence gives way to interstellar space, the last telescopes capable of tracking it captured final images. The comet appeared as an almost featureless point of light, its coma nearly gone now that solar heating had weakened to negligible levels. Within months, it would be completely undetectable, too faint and too far for even the most powerful observatories to see. And then it would be gone, returned to the darkness between stars, carrying with it the marks of its brief passage through our neighbourhood. Somewhere in the next star system, 3i Atlas approaches. If there are astronomers looking at the right time in the right direction, they might detect a faint visitor arriving from the general direction of our Sun. They might study it, document its composition, debate its origin, and wonder about the stellar system it passed through so long ago. They might, without knowing it, be examining traces of Mars carried across light years of space. The thought is almost unbearably poignant, a connection across distance and time that no conscious agent arranged, but that the universe made possible through its patient, indifferent operations. We've journeyed together through the story of what happened when an interstellar visitor named 3i Atlas swept past Mars in an encounter so rare that it might not happen again for millions of years. We've examined the observations, the data, the careful scientific analysis that revealed how cometary material from another star system reached the red planet's atmosphere. We've explored the implications, the speculations, and the persistent questions that linger even after months of research and analysis. But now comes the part of this story that hasn't been written yet, your part. What do you make of all this? What questions does it raise for you? What possibilities does it suggest about our place in a universe where boundaries between solar systems turn out to be permeable, where worlds can be touched by travellers from stellar neighbourhoods so distant we can barely conceive the separation? This isn't a rhetorical invitation. The story of 3i Atlas and Mars isn't finished because no scientific story is ever truly finished. Every answer generates new questions, and some of the most important advances in understanding come not from people who simply accept established conclusions, but from those who ask what comes next, what else might be true, what alternative interpretations might fit the evidence. You don't need a PhD in planetary science to contribute meaningfully to that conversation. You need curiosity, willingness to think carefully about evidence, and the courage to articulate ideas even when you're not certain they're correct. Some of the best scientific insights have come from outsiders, asking questions that experts had stopped asking because the answers seemed obvious, until someone demonstrated they weren't obvious at all. So let's think together about the mysteries that remain. Start with the most fundamental. Where exactly did 3i Atlas come from? We know it originated beyond our solar system, but that's like saying someone comes from Earth without specifying which country, city, or neighbourhood. The comet's trajectory when it entered our solar system pointed back toward a general region of the galaxy, but tracing that trajectory backward through millions of years of travel requires accounting for gravitational perturbations from every massive object it passed near, the subtle influence of the galactic tide, and even the tiny pressure from starlight accumulated over eons. The uncertainties compound rapidly. Current estimates suggest 3i Atlas might have originated from somewhere in the general vicinity of the Cygnus or Lyra constellations, but that's an area containing thousands of star systems. Did it form in orbit around one of those stars and get ejected by gravitational interactions? Was it born in a stellar nursery that has long since dispersed, so the star system it came from no longer exists as a cohesive unit? Could it have been wandering the galaxy for so long that its birthplace has moved halfway across the Milky Way from where it started? Here's a question worth pondering. What would we need to answer that origin question definitively? Better trajectory data would help, but there are hard limits to how precisely we can track objects over interstellar distances and timeframes. Perhaps the answer lies in the comet's composition. If we could analyze its isotopic ratios, the relative abundances of different atomic weights of the same element, in exquisite detail, we might find fingerprints that match specific stellar environments. Different stars produce different isotopic mixes depending on their mass, age, and history. A comet that formed around a low-mass star might have subtly different isotopes than one that formed around a massive star. We have some compositional data from 3I Atlas, but not at the resolution needed to make these kinds of discriminations. Future interstellar visitors might provide better opportunities, especially if we can send spacecraft to rendezvous with them for close-up analysis. What would it take to make that happen? How quickly would we need to detect an incoming interstellar object to have time to plan, build, and launch an intercept mission? These are questions that space agencies are beginning to seriously consider. Another unresolved question centers on long-term effects. We established that 3I Atlas likely deposited trace amounts of material into Mars's atmosphere and possibly onto its surface. Those atoms are still there, mixed now with Martian dust and atmosphere, in concentrations far too low to ever detect directly. But what if we could detect them? What if future Mars missions include instruments sensitive enough to identify isotopic or chemical signatures that don't match native Martian material? The challenge would be distinguishing three I-Atlas derived material from all the other exotic material that has accumulated on Mars over billions of years from meteorite impacts, solar wind, and cosmic dust. But suppose we developed techniques sophisticated enough to isolate interstellar components. What could we learn? Could we use Mars's surface as a natural archive, a place where interstellar material has been accumulating for eons, creating a geological record of cosmic visitors that extends back to the planet's formation? The idea sounds far-fetched, but so did many things that are now routine. Curiosity and Perseverance rovers regularly identify and analyze individual mineral grains. Why couldn't future instruments identify grains of interstellar origin? Think about the human dimension of the encounter. Why do stories like this capture our imagination? We've never visited Mars ourselves, only robotic proxies have walked its surface, and most people will never look through a telescope powerful enough to see 3I Atlas, even when it was at its brightest. The encounter happened millions of kilometers away, involved processes we can only study through electromagnetic radiation and mathematical models, and had no direct impact on anyone's daily life. Yet it mattered. It generated news coverage, scientific papers, educational programs, and now this extended exploration of what it all means. What need does this story fulfill? Perhaps it's the need to feel connected to something larger than ourselves, to be reminded that we're part of a cosmos that extends beyond our immediate concerns. Perhaps it's the thrill of witnessing something genuinely rare and unprecedented, an antidote to the feeling that everything has already been discovered and documented. Perhaps it's hope, the recognition that if comets can travel between star systems, then maybe someday we can too, that the galaxy isn't forever beyond our reach. Let's also consider the controversies and the rumours we discussed earlier. Even after reviewing the evidence, some people will remain convinced that there's more to the story than official accounts reveal. What do you think drives that conviction? Is it purely distrust of authority, or is there something else, a deep-seated intuition that the universe is stranger and more meaningful than mainstream science allows? Here's an interesting thought experiment. Suppose some of the wilder speculations were true. Suppose 3I Atlas actually was an alien probe, or suppose it did trigger lasting changes on Mars that scientists haven't yet detected. How would we know? What evidence would we need to be convinced? It's easy to dismiss unfounded speculation, but it's harder and more valuable to articulate what would constitute genuine evidence for extraordinary claims. This is how critical thinking works, not by rejecting all unconventional ideas, but by being clear about what would change our minds. Consider too what the 3I Atlas encounter suggests about how special or typical our solar system might be. We've now confirmed several interstellar objects passing through our cosmic neighbourhood, and statistical estimates suggest these visitors are far more common than anyone suspected even a decade ago. If objects regularly travel between star systems, then material exchange across interstellar space isn't a rare exception, but an ongoing process. Every solar system, including ours, is constantly being contaminated, in the scientific sense, with material from elsewhere. Organic molecules, complex chemistry, perhaps even the building blocks of life are travelling between stars, carried by comets and asteroids ejected from their birth systems and wandering until they're captured or destroyed elsewhere. What does this mean for the question of how life originates? If prebiotic chemistry is being distributed throughout the galaxy, does that make life more or less likely to be common? Does it suggest that life might share common ancestry across interstellar distances, seeded by cosmic visitors like 3I Atlas? These questions venture into speculation, but they're grounded in the real observation that interstellar exchange of material actually happens. What about the future? How will the 3I Atlas encounter be remembered a century from now, or a millennium from now, assuming human civilization persists that long? Will it be a footnote in the history of astronomy, an interesting but minor observation eventually superseded by countless other interstellar object encounters? Or will it be remembered as a pivotal moment, the beginning of a new era when humanity started seriously studying visitors from beyond our solar system and recognizing the connections between stellar neighborhoods? The answer depends partly on what happens next. If 3I Atlas remains an isolated event, exceptional but not transformative, its historical significance will be limited. But if it's the first in an accelerating series of discoveries, each one revealing more about the nature and frequency of interstellar visitors, then future historians might look back on this Mars encounter as the moment when we began to understand that our solar system is not an island, but a port of call in a much larger network of cosmic exchange. Here's what I want you to do. Take a moment and think about the single most interesting or surprising thing you've learned from this exploration of what 3I Atlas did to Mars. Maybe it's the fact that atoms from another star system are now part of Mars's atmosphere. Maybe it's the realization that interstellar objects pass through our solar system more often than we thought. Maybe it's something about the process of science itself, how researchers from multiple countries coordinated to document the encounter, or how careful analysis can extract profound insights from subtle signals. Whatever stands out to you, hold on to it. That's your anchor point, the thing that connects this story to your own understanding of the universe. Now consider what questions you still have, not vague wonderings, but specific questions where you genuinely like to know the answer. What aspect of the encounter remains mysterious or incompletely explained? What would you want to investigate if you had access to all the data and resources? What future observations or experiments would you prioritize? Articulating these questions is valuable not just for your own understanding, but because the questions that non-experts ask are often the ones that open new research directions. Scientists can become so immersed in technical details that they lose sight of bigger questions that seem obvious to outside observers. Your perspective matters. Finally, think about what this story means for how we see ourselves and our planet. Earth hasn't been visited by a confirmed interstellar object during recorded history, or if it has, we didn't recognize it as such at the time, but statistically it has certainly happened in the past, and it will certainly happen in the future. Comets and asteroids from beyond our solar system have struck Earth, contributing their exotic chemistry to our planet's inventory. The water in your body, the carbon in your cells, some vanishingly small fraction of it might have interstellar origins, carried here by cosmic visitors over billions of years and incorporated into the web of life. Does knowing that change how you think about your connection to the wider universe? Does it make the cosmos feel more immediate, more relevant, less abstract? Or does the scale remain too vast, the connection too tenuous to feel meaningful? These aren't questions with right or wrong answers. They're invitations to reflection, to taking the information we've explored and personalizing it, making it part of your own understanding rather than just facts you've learned. The story of 3I Atlas and Mars is a story about connection across impossible distances, about how worlds influence each other in ways that transcend borders and barriers. It's a story about curiosity, about the drive to understand even when understanding is difficult and the answers are incomplete. It's a story about what becomes possible when people work together toward a common goal. And now it's your story too, because you've taken the time to engage with it, to think about it, to make it part of how you understand the universe we all inhabit. So here's my final challenge to you. Share this story, not just the facts, though the facts are important, but what the story means to you. Talk to someone about what happens when a comet from another star system passes close to a planet, about how scientists detected the interaction, about the questions that remain unanswered. See what questions they ask, what aspects of the story capture their imagination. Because ultimately, stories like this matter not just for the knowledge they contain, but for the conversations they generate, the curiosity they spark, the sense of wonder they preserve in a world that often feels too mapped and understood. The universe surprised us with 3i Atlas. It reminded us that there are still first times, still unprecedented events, still opportunities to witness something that has never happened before in human history and might not happen again. Don't let that sense of possibility fade. Carry it forward. Ask questions. Stay curious. Keep looking up. The encounter between 3i Atlas and Mars is over, but your journey with this story continues. Drop a comment below and tell me what aspect of this encounter fascinates you most. What do you think really happened when that interstellar visitor swept past the red planet? What questions do you still want answered? And if this exploration opened your eyes to just how connected we are to the wider galaxy, how the boundaries between here and there are more porous than we ever imagined, then share this with someone who needs to remember that we live in a universe still capable of astonishing us. The cosmos is vast, ancient, and full of wonders we're only beginning to understand. 3i Atlas reminded us of that. Don't forget.